All right, so just to hone in this or drive home this idea of class invariance, let's take another example at a toy representation, a toy concept as rational numbers, and again go through the exercise of identifying what the class invariants are, and then we'll applying this notion of the class invariance reasoning principle. And let's take a look at three different implementations, right? Compare them against each other, and see how successful, right, each one of these three different implementations are at keeping having the methods guarantee that the invariance is never broken, right? And see, even in such a trivial example, right? One might think that these methods might be able to guarantee these things, right? Uh, so, so rational numbers, right? Rational numbers are you have a numerator, you have a denominator, and so there's quite a few different operations that you can do on them, right? You can add them, you can multiply them, and usually some of these operations are easier if you reduce the rational numbers into some greatest by reducing the numerator and denominator by using the greatest common denominator, right? You are able to divide them and have them in some canonical format, yes? And depending on how you represent them, things are easier or harder, right? On how to apply some arithmetic operations on rational numbers, yes? So anyway, so we have typically we represent them by using some numerator and denominator, okay? And there's several ways that we can implement them. All of them are going to rely on this idea of representing with numerator and denominator, but they're going to change slightly. The implementation is going to be slightly different. We'll see that they progressively decide, right, to how to guard against the invariance, right? We'll first spread out the guarding of this invariance across multiple methods, right? And that will make it much harder, right, to maintain these invariants, right? Because it will be spread out across multiple methods, and we'll progressively make decisions at trying to concentrate or modularize the guarding of these invariants, right? So that instead of having to maintain 3, 4, 5, 6 different methods, perhaps we only have to maintain just one or two, right? And once we can guarantee that we have a particular representation, all the other methods will become trivial, right? All the other methods will just assume that I am in a correct state. Right? I don't have to do much to transform my data into an equivalent valid state, right? Because we have taken all the guarantees into one single set of methods that are the ones who we can rely on. I just have to make just my work becomes smaller. I just have to make sure I don't screw up. Right? If all these methods I can rely on these, right? My work is very simple. So let's take a look at the interface that we're trying to implement, right? So we have this data type that represents the rational number, a rational number. We can certainly want to be able to compare a rational number against another rational number. This might be this might look trivial, but until you start considering that you want to compare 2 over 4, right, should be equal to 1 over 2. Even if the numerators and denominators are different between these two rational numbers, they are logically the same. Yes? So right there's a wrinkle on how is it I'm going to compare these two things, right? How is it I'm going to represent them and decide also, these might be, dividing, how do you validate that 1 over 3 is equal to, or should be logically the same as 0.33333, infinite, yes? There's rounding errors, there's, how far do you want to go back to compare these two things to say that it's the same, yes? So there's some wrinkles in here on what is that how are you going to compare these two things. It depends on how is that we represent the numerator and the denominators. So anyway, so we have the this interface, this trivial toy interface. But nevertheless, will have its challenges. You know, imagine something real, right? It's having much more challenging things to consider. So we have two methods that allow you to read what the numerators and denominators are. One of them that allows you to compare the double value, that allows you to retrieve the double representation of actually dividing the numerator over the denominator. Also, we want to be able to do some trivial arithmetic of being able to add the current rational number plus some other rational number that you pass me. We have multiply, again, multiplying the current rational number times some other rational number that you pass me, and negate. So these are going to be some. These are all the what we call the domain methods, right? These are methods that are specific to the domain. In this case, the rational numbers is the domain we're looking at. There's a whole bunch of other methods that are not part of the domain, right? There are the standard methods such as equal, right? ToString, hash code. Those two need to be implemented. Yes. So we'll look at first, the domain methods. We'll look at the standard methods. And see, depending on how we decide to represent them internally, what changes, how our decisions of consolidating the class invariance, how does that affect the implementation of other methods? So let's look at a first implementation. This is again, all of these are trivial, right? They're very easy. They have enough complexity for us to to be able to just to present the principles, right? But they're not too complex that it just makes it unwieldy. So our first one, right? We are, it's fairly a naive implementation, right? It's something that most of us would do, and we're going to concentrate our validation of our denominator and our numerator and denominator. We're going to validate, make sure that our denominator is not 0, right? We're gonna validate all that at the constructor, right? That's a fairly trivial way that we would all mostly implement, right? Just validate that at the constructor, everything's okay, and then just have everybody else just validate and make sure that we don't break that invariance, that we never have the denominator being 0, and we'll look at the implementation of all the other methods, right? They're going to assume that the constructor was doing its job, right? The denominator was not 0, right? And then the responsibility of each one of these methods is to make sure we don't break that invariance, right? That we don't ever have the denominator equal to 0. Also, they are aware that we have different ways of representing rational numbers. Right, that indeed 2 over 4 should be equal to 1 over 2. Right, so we're going to have all the methods be responsible for making sure that they all know this fact, right? That there's different ways of representing them, right? So each one of these methods will be responsible for converting each numerator and denominator to a greater common, divided by greater common denominator, to make sure that we were able to compare them, we're able to add, multiply, divide using this fact. Yes. Right. So here we have the two constructors. Notice that we are representing the numerator and denominator using a big integer. Big integer is a Java class that allows us to represent arbitrarily large numbers. Right. If it doesn't fit, it just keeps adding, using bigger and bigger representations. We have a base implementation for the rational implementation 1, our first version. We're going to look at 3 different versions. So here we have concentrated our validation that we don't have an invalid rational by validating that our denominator is not 0. And I guess we should this should be D d. And we validate that the denominator that comes in as an argument is not 0. And if it is, we throw an exception. And if everything's okay, we just update the numerator and denominator. Fairly trivial. And then we have the other constructor. This is a convenience constructor that we can initialize it with two longs. And then it just reuses that constructor. Yes? Right? There's nothing wrong with this. We'll revisit this in a minute and see what would be an improvement over this. All the other ones are fairly simple. We, the numerator and denominator, and make sure that we can we represent the numerator and denominator in some canonical format, right? That we divide the numerator and denominator by a greater common denominator, right? So make sure that we reduce 2/4 down to 1/2. Yes, right. So that we always have some canonical representation, right? And here we have it. We have the numerator and denominator both doing the same thing, right? Identifying what the greatest common denominator is, and then dividing it so that we can reduce it down to a common representation, right? Let's see. We have a double value. The double value just does the actual division, right, of dividing the numerator and the denominator, and returns a double representation. Negates. Notice that all these, the GCD function, right, and the dot divide function, those are all methods that are declared on big integer. Yes, big integer knows how to divide two big integers, how to negate them, how to divide them, how to multiply them. So we don't have to implement that, right? These are not integers. These are not long. These are huge numbers. So multiplying them requires their own arithmetic, right? So GCD, divide, all these are declared on big int. Yes. Dividing. So negate is also declared on big integer, right? It just changes the sign on it. Addition. This is just some simple arithmetic. Nothing wrong with this, right? It makes sure that we reinstantiate a brand new version of this rational in terms of how you normally would multiply two integers, right? So there's nothing wrong, no trick here, right? It's just knows how to multiply denominators and numerators to get a new rational number, which is equivalent, right, to the. But notice what it does not do, right? It does not convert them in. It does not reduce them, right? It does not reduce them. It just leaves them in their new representation. It is the numerator and the denominator methods, right, who are responsible to then, right, reduce them into their equivalent format. Yes, right. So notice that it's not the constructor who's doing this. It is the numerator who are doing this, right? Which we'll come back to and point out that that's a flaw. In our implementation, right? That we are delegating all the responsibility of this conversion back and forth, right? Across multiple functions, across multiple methods, and that's going to make our code brittle, right? That if we have to change the implementation, we're going to have to update multiple methods, as opposed to maybe concentrating this in some one place. Multiply, the same thing, right? We just multiplied blindly the numerator with the denominator. This denominator with that denominator, right? No difference there. Equals. Also, it makes sure that to compare that these are equal. I'm just going to multiply I'm going to just cross multiply and see if I get the same value, right? If I have the same value, then they must be the same, right? They're equal based on the denominators and the numerators, right? So again, just some simple arithmetic. Always the boilerplate first couple of if statements, right? The obvious one, right? If they're the same pointer, then obviously they're the same. If they're not the same data type, then why bother comparing them? They're not the same. And then there's the actual comparison, the logical comparison on whether these are truly the same, based on our logic of our understanding of what we mean things to be the same. Yes? We have hash code. Hash code, converting first, representing things into its greatest common denominator. and then calculating the hash code on both of them. And finally, compare to so that we can compare whether something they're equal, greater than, or less than, so that we can sort these big integers, right? And again, doing multiplying to see the who's bigger, who's smaller, either this or that or the other, right? So nothing too crazy, nothing too crazy. A two-string, it is doing the reducing, right? It's calculating the greatest common denominator, converts everything down to its smallest representation, so it converts down, 4/8, right? Reduces them down to 1/2, so that we can always represent them with in its slowest format, right? So there's nothing wrong with that implementation. But one of the things that we were pointing out is that it's is the fact that we don't have a canonical representation, right? We have spread out the logic of converting back and forth using the GCD in multiple methods. We would like to concentrate that, right? If we do that, hopefully, perhaps, all our other methods might make it easy for them to guarantee that the denominator is not zero. That we have one single representation. First of all, what we're going to do is that we're going to take out. We're going to refactor some of these guarantees of this initialization. Instead of putting it in the constructor, right? We're going to instead we're going to factor that out into a private. Into a public factory method, right? Whose only job is to guarantee that we start at an initial state. So we're going to take all that logic, we're going to break it out, right, and take it out, and then our constructors are not going to be the responsibles for enforcing anything, right? Instead, they're going to assume that whatever you give it for constructing, they're already been verified, that I can trust the values that I'm being passed already, right? That I don't have to do any validation whatsoever. I'm already at an initial state, right? So let's take a look at this first version, right? So first of all, we're going to notice that our constructor, we're going to make it private, right? So no longer are you going to be allowed to just call this constructor with whatever you want, right? Instead, we're going to force you going through some logic that is going to do all the validation. Now, our validation is trivial, right? Just checking to see if something's not negative, yes? But in something much more complicated, right? The logic might be fairly complex, yes? And it's usually a good practice, right, to encapsulate that logic into a function that you could call it multiple times, right? That you don't require instantiating anything. You can just call it. Right? You can invoke it from several places, not just the constructor. Yes, and that's what we're going to do. Right? We're going to make the constructor private, right? And instead, we're going to rely on the factory pattern that we looked at a couple of weeks ago. Maybe at the beginning of the course. Right? We're going to rely on factory methods that we're going to rip out the logic from here. We're just going to put it in a public function. In this case, we're going to call it create. Notice that it has the same signature as our constructor, right? Well, except for the name, right? It's called create. We pass in the two big integers, and we do the check. We validate that something's not zero, and if we pass this initial class invariance, right? We go ahead and instantiate it for you, right? We instantiate it, and so. So this is the gateway, right? This is the only way that we're going to be able to instantiate this. We can't directly call it. So now the rational, our constructor can now be trivial, right? No longer does it need to do any validation. It can trust that whatever you pass it already is in a good state, right? I don't have to validate anything. Perhaps we also have a convenience factory methods that can take just two longs, right? Numerator and denominator. And then it relies on the all argument constructor to convert them into big int values and just represent them represent them in big int versions of this, right? Everything else stays unchanged, right? The same. We still have the same problem as before. We still have add and multiply and and toString and equal. They all still have the problem of converting using this GCD, the greatest common denominator, spread over multiple different places. Yes, we still have to deal with that, but at least we've made just one incremental improvement. Right? We've encapsulated this logic of the invariance in one single place that could be reused. Right? I can just run this create and make sure that what I get back is a valid initial state. So let's move forward a little bit. We have this additional incremental improvement of a third version of this trivial class, right? That what we're going to do is that we're still gonna have the constructor be private, right? Nobody can directly access this constructor. We're still going to go through a factory pattern, but we're going to break out some of what we had earlier of converting things into using the greatest common denominator and whatnot. Instead, what we're going to do is that we're going to do that from the beginning, right? And we're only ever going to represent our numerator and denominator using a canonical format. Yes. So instead of spreading out this conversion of using the greatest common denominator all over the place in our source code, we're doing one single place, right, at the very beginning, right? So all the other methods, instead of them having to validate and muck around with greatest common denominator and whatnot, right, they can rely that this has already been done, right, and that I already have this representation in its lowest reduced format. And I don't have to, they become trivial, right? So we have the rational implementation. We still have the numerator and denominator. We're now introducing, we're going to apply the invariance, right? That whenever I access this numerator and denominator, they are always represented in its reduced format, right? Before that invariance was being enforced by each method. Right? Each method was responsible for enforcing this invariance, right, by reducing down using the greatest common denominator. Now I'm going to document it. I'm going to document it that those are the two invariants, right? That there's no smaller greatest common denominator, right? That is always 1. Right, that there's nothing smaller than that, and so we're going to break it out. What we're going to do is that we're going to push down the responsibility of the numerator and denominator, and we're going to just push it down to a different layer of abstraction. We're going to say, well, check, verify that the numerator and denominator, enforce the following the following constraints, right? And it's going to validate that that's 0, and it's also going to be responsible for converting the numerator and denominator into its reduced format. Right? We know that we need to reduce this. Ideally, this happens only once. Right? Perhaps we have a method that does this. You pass the numerator and denominator, and it updates the state into its reduced format. Okay. So we're going to encapsulate this into a function called trust that is going to be responsible for implementing this this invariance. Where is it? It was somewhere in here. Where are you? Oh, here we go. Sorry, I have the slides in a slightly different order than I wanted. Yeah, here's the reduce. So the check comes down to here where we do. First, we validate our first invariance, right? We don't have a 0 denominator. And then we're going to enforce the second invariance, right? That our representation is always in a reduced format. We pass in the numerator and denominator, and it's here we have centralized in one single place the update that we're going to divide the numerator by its greatest common denominator, and both the current values of the numerator and denominator are going to be implemented in its lowest common factors. Yes. So now that we have concentrated our representation into a canonical format, right? None of the other methods have to muck around with GCD or of dividing by the greatest common denominator. They become trivial. Right? Our equal already can assume that the numerator and denominator are already in its reduced format. Right? I don't have to do any of that. They become a trivial implementation. I just need to validate that they're equal. That the numerator is equal to that other denominator. I don't have to convert them into any canonical. They're already in the canonical format. Same thing with hash code, right? I already assume that the numerator and denominator have already been reduced. Right? There's no point of me doing it here. Same thing with toString, right? My validation is trivial. I already know that I'm relying on the fact that they've already been reduced. Right? I just have to make sure that when I leave this here, I don't do anything to change that fact, and I don't. Right? Equals doesn't, toString doesn't, hash code doesn't. Right? They don't update anything. They don't do any transformation whatsoever. All right, so let's take one more example.